So the last time, what we were doing was we were proving the equivalence of this statement and this statement. And we've already done the zero here. And in fact, we did the first part, but for completeness, it's not gonna hurt anything. I'll go through this in its entirety. Proof of this direction here. So I know that for every R module D, this is an exact sequence. I need to show that this one is exact. This is what I showed last time, but it might help us maybe if I can go through it again. Why is G onto? Well, the key to doing this direction, I've got freedom on what my R modules need to be. So what you want to do is pick these sagaciously. So I want to select D to be C mod the image of G, and let pi in home C to C mod image G. Be projection. Phase pi C is C plus image. Set coset. Right. Now note. If I do, when I do, see where does G go from here? Yeah. So when I do G then pi, this should be zero now. Right? Because G takes B, it goes into the image of G, and this takes everything in the image of G to zero in the next step. And this is, of course, G bar by definition. Right? So this means since G bar pi is zero, this means that pi is in the kernel of G, which is equal to the subject this turned around. Forgot this is contravariant. This is in the kernel right. This is in the kernel of G bar. The G bar is 1 to 1. So pi is the zero homogeneous. Where pi goes, you see C mod image Q. The only way this is a zero homomorphism for all C and C. C is in image of Q. So G is on G. So this G is on G. Now I've got two other things to show. I need to show that the image of F is contained in the kernel G, and kernel G is contained in the image of F. Right, of course, I've got no obligations on that one. So let's do image of F is contained in the kernel. In this case, what I want to do is I'm going to pick so I have And I'm going to select and let me not confuse the notation too much, but what I mean is this is the identity on the amorphous and it takes everything in C to itself. Notice that if I do, well, to one C, if I do G bar and F bar, this is zero. It's zero anymore because I know this is exact, so the kernel of G bar is contained in the image of F bar. But what is this exactly? Well, this is by definition. So since FG is equal to zero, this implies image that is containing kernel. So the final piece of the puzzle is to show the other containment. I want to show that the image of, the kernel of F bar is contained, or the kernel of kernel G is contained in the image of F. And this time, it's I'm going to take D. B mod. So and then somehow I want to get the kernel G is contained in the image of F. Let's let pi be given by pi of B plus A. So again, Gina just kind of did the natural, what you would guess. Note that what happens when I do F and then pi? Well, you start with F and it goes, the image of this, it's the image of F. When you hit pi with that, you're going to go to zero. Just because of the way that I set this up. And of course, this is F bar pi. So pi lives in the kernel of F bar, which we know is the image of G bar. So if it's in the image of G bar, hence we can find let's call it gamma and home are C to F such that U bar gamma, which is gamma G, is equal to F. Right, okay. So let's see, where does G start? So if B is in the kernel G map here, let's see what this tells us. this means that F and gamma P like here. So if B is in the kernel of G, then gamma GB is 0. Oh. So remember what I'm going for. This is pi. It was pi all that. I don't know why I wrote that down. I freaked out. That's pi. So if B is in the kernel of G, then gamma G B 0, which is pi, or I'm sorry, pi, right? Since pi B equals 0 plus image there, this implies B is an image set. Therefore, kernel of G is go. Okay. Any questions on that? So y'all kind of see that, you know, there's a little bit of art to this, right? You've got to pick your D's, makes it work out. You'll get the chance to do this in the homework, and I hope it's a little easier because I gave you all the covariant, so you don't have to worry about the changing of order like we did here, although it's not. Okay, theorem. Let me actually before I do this, actually. Let's look at some exact sequences. Look at okay, so this is the exact sequence where I'm on my input, double it, and then my map from here to here just reduces my two. Like, it's easy to see this exact sequence. What happens when I home this, right? Let's home this and see. Let's see. Home. Um, uh, and this is what I mean by homing them. So notice I kind of fill in the blanks here. Okay. So what happens? Well, I know that should be 1-to-1. Everybody agree with that? Is this on to? Well, the answer is in this case, yes. Anybody know what this is isomorphic to? Mike, Right. This is actually isomorphic to Z. This is isomorphic to Z. And this is isomorphic to Z minus Z. And the isomorphism comes with homework problem already done. You should probably check that this exact sequence basically bars out the same. Four, right? So it turns out for this one, yes, it's still exact. But what if you do the other columns? What if you apply well, by our theorem, we should get 0. What should I fill in here? This one has a little bit different character. This one is E1 2, right? Quite remove. Now, what can you say about this? What are the homomorphisms of Z2 and Z? There's only one, only 0. Right, because remember, this is a finite group. So in particular, any element has finite order. The only element can see a finite order is 0, so everything has to become 0. This is isomorphic to Z, and this is isomorphic to Z. This map, as predicted, is 1 to 1 in a very silly way. It's 0. And the image of this is equal to the kernel of this. So this one's 1 to 1. Might check and see if that was on. Given the original induced homomorphisms. Okay. Any questions? Another example. Right. Probably this exact sequence here. Simulation sequence. Well, these maps are inclusion and just projection. Home this with Z and home with Q in both directions. By the way, I'll leave this as an exercise. Home this with Q and Z in both variables to see what happens here. So the point, one of the points of this example is, for example, you don't always get onto, you don't always, so it's not always exact when you start with an exact sequence. But I noticed that sometimes it is. For example, this one remains the exact sequence. So here's an important large class of exact sequences where this works well. There. Let's let A, B, C, the R modules. The following are equivalent. Number one. Is split exact. Split exact is super strong. Two. Is split exact for every R module D. Would be R modules. And three. Good. So split exact is all good, right? By the way, here's a little teaser for what's ahead. Here's where home can behave well. Does anybody know a type of module called C where this is always split exact? Projective. Right. So think about what this means. For example, if C happens to be projective, then any short exact sequence splits. And if A is injective, then every short exact sequence splits. So think about what that means. We'll see a little bit of that later. I'll show one and only two, and I'll leave the others for an exercise because again, that's kind of similar. So for one implies two, we know this is split exact, and in particular, we know it's exact. So we already know zero and home in A, home in B, home C is exact. We already know that, right? So my burden is a little bit less. There's really two things I got to show. I need to show that this is exact, which means the G bar. I need to show the G bar onto it. And I also need to show the fact that this is split exact. All right, so I need to find the splitting here. So I can do this in one fell swoop as follows. there exists H bar from home R PC to home R B such that when I do H bar, B bar, it's the identity on homes R. And let me just quickly remark, this is the splitting, and since GH bar is onto G bar onto. So I just make this remark because this composition here, this thing is onto, so that means that the last member has to be onto. So really all I need to do is get the splitting here. I just need to get this H bar, I should say, that goes backwards and gets to what I want. Since 0, A, B, C, 0 splits, there exists an H and I claim that that induces exactly what I want. So H bar, home bar, PC, home bar, PD. And remember how this animal works. If gamma is in home R, DC, that means and then we compose this with whatever this thing was. Uh, then H bar gamma is equal to nu gamma then H. And so notice if gamma is in home or DC, right, then if I do this is G bar of H gamma, which is G H gamma, which is GH gamma, which is 1C gamma. So in particular, what we've gotten is so sequence. Little sequence. So let's get the other direction. 2 implies 1. So you know that for all D, Just as before, we've already got some of the work done for us. We already know. Zero. We've already got that much. So what we need is G is on two and it's splitting. So it's the same kind of thing. So let's let D equal C. And so we now have R C A home R C B home R C C. And let's let B from C to B. So it's that G bar of B is that. Right. I know that this is exact. In particular, this is on. And I know over here somewhere is the identity function on C, correct? So there has to be some B here that goes to the identity function on C. And I will find that animal. And so let's look at our exact sequence. So you have 0, A, B, C, 0. You have, well, let me know. What we have here is C. And we know that doing G and then doing phi is the identity. I'm sorry. Doing phi to G is the identity of C. So G is on two. And phi is our split. So yes, that's right. It's on two. And it's splitting. There you have it. Okay, any questions? Any questions? That's fine. Okay, I have kind of another dueling pair, projected and injected theorems. And something I felt. So I'm going to report both of these, and we'll talk about them. The first one, theorem 674. Let E be arm. E is projective. If B from B to C is on to, then the induced phi bar is on to. So if it's projective, then the induced, it preserves alterness when it induces maps. If 0, A, B, E Here's the short exact sequence. Then zero and home are a home are beginning home are these in times E F is a short exact sequence. As you might guess, I'm gonna put this in the other order. There's a injective partner to this. The following conditions on the R module I are equivalent. A I is infected. B if B is more than one, then so is this not so this. Very good. Right. Versus rolls one point onto. And if you have a short exact sequence, here, zero A, B, C. G is short exact sequence. Then so is so you see these theorems look uh very similar, right? P is projective, it means this is onto, if this is onto, then the induced map is onto, which gives, if this is a short exact sequence, and so is this. Right, notice that B implies C is pretty straightforward. Let's prove this. We'll prove the projective. Okay, so for this one, the objective, we need to show that this is onto and the home is onto. I'm going to basically use the definition of objective here. So suppose we have this. Where we have this is onto. Um. Let's call this alpha. So what I'm trying to do is I'm trying to show that this is onto, right? So let's let alpha in home R B C. I'm trying to show that everything here is covered by phi bar. So alpha is an arbitrary element of home R B C. Put in my diagram here, but P is projected. So there exists H and PB. Translation, H is in home R PB, such that when I do H, then I do phi, which is P bar of A, and get alpha. So P bar is on. Okay, so someone, so let's do B and plus A. So I have this thing is onto. If this is onto, then this is, so I need to show the P is projected. So suppose we have diagram. And I call this alpha. Now, my goal here is to show that P is projected, right? So I have to show that there's a lift here. What do I have? I know since P and B, C is onto, then P bar from home R, PB, and home R, PC is also on. Well, notice that alpha is in home R, PC. So there exists H in home R, PB, such that B bar H is alpha. But of course, the induced map is DH. So that means that can complete this diagram. So if okay. Okay, questions? Okay, so let's do B and plus F. This says you have an onto map, and this is onto. So yes, it is pretty immediate. If 0 A B, C, 0 is a short exact sequence. So in particular, then so is 0 on PA on PB on. We already know this. We already know this. It remains to be shown G bar on. Right, but now it's needed. But since G from B to C is onto, so yes. So there you go. So the only missing piece of the puzzle is the onto-ness of the last map. That's precisely the statement B. And we will finish this with C implies B. So so we know that if we ever see a new exact sequence, this form get tail in, then you get a short exact sequence on here. Fine. So suppose that the from B to C it's onto. We have short exact sequence given by B to C. This is onto. And how would I finish off the short exact sequence? With the other pieces? So then, yeah. That's the easiest way to put the front on this. There you go. So this is a short exact sequence. So because that's a shame. This should, I don't know why I wrote this here. This should be a. See, it's a good thing about doing proofs. If I wrote I there, I don't remember if I did it or not. If I wrote I there in 6, 7, 5, that should be a 6. But I don't know where that thinking. I'm glad I did the proof because I saw it. Now this should be any C. This doesn't have to be P at all, and we haven't used any of that yet. So what do we have here? And the proof. So we have phi from B to C is onto, and so now we've got this short exact sequence that we've built. So this gives us a home E or phi into home E B into home E C. Is a short exact sequence. By hypothesis of C. And so therefore, B bar and home R B into home R C is on. And that concludes theory. Any questions on that? Any questions? All right, well, I'll just have to dust up a few things next time before we move on with the tensor product. If there are any questions, y'all have a good one, and we'll see you on Wednesday.